Next, we will talk about the smart manufacturing solution. Let's start with the stages of new industrial revolution. The first industrial revolution was about mechanization, followed by electrification and automation. Now it is the fourth one, that is intelligence. In this phase, new ICT technologies such as cloud computing, big data, IoT, and artificial intelligence can be combined to reshape information flows, capital flows, and logistics to improve production efficiency and business development. But what are challenges in the digital transformation of the industrial field? Specifically, in the current phase, wired networks are predominantly used in the industrial internet to support on-cloud production. However, for wired networks based on network cables, optical fibers, or others, there are some common problems, such as long cabling period, poor scalability, poor resistance to corrosion, high cost, and a complex O&M. In addition, the standards and the products are highly monopolized, so the wired connections can be costly. For wireless communication, for example, Bluetooth for asset management supports only a limited number of connections and short distance, and it cannot meet differentiated application requirements. Another wireless solution is Wi-Fi, which is used for AGV dispatching. Its spectrum is unlicensed, so it cannot provide a reliable performance, and it has security risks too. Industry private wireless networks as well, despite their reliability and feasibility, they have a narrow industry chain and entail high deployment costs. Moreover, the public cellular network such as 4G is used to implement remote monitoring. But the 4G connection capability is low and a lack of high real-time performance, and data needs to be transmitted through the public network, posing security risks. And to sum up, existing solutions are costly and poor in scalability and cannot greatly meet the high security requirements of the industrial internet. This calls for a new communication network that features wireless connections to the industrial internet. With this new wireless communication system, manual operation can be replaced by automatic devices in favor of reducing costs and improving efficiency. Industrial buses can be replaced by 5G networks to promote flexible manufacturing through wireless connections. This new communication system will also ensure that the algorithm part of devices can be deployed on the cloud to achieve low-cost, faster iteration. As such, this new wireless communication system can meet the service requirements of the industrial internet. The new wireless communication system is just a 5G. Let's take a look at some 5G-enabled applications of smart manufacturing. The first is remote control of robotic arms based on the highly reliable 5G network. It requires an uplink rate of at least 10 megabits per second to upload data to the cloud and the control end. As an application in the production scenario, it also has high requirements on reliability. For the coverage scope, only the production line needs to be covered. Robotic arms are connected to 5G base station through 5G modules or industry wireless devices. Then, data is uploaded to the edge data center or the industry cloud platform, implementing the control of robotic arms. This can be achieved in real time. In addition, 5G networks replace wired networks that connect to robotic arm programmable logical controller, PLCs, enabling flexible manufacturing in the factory. Also, robotic arms can be flexibly adjusted to meet customized requirements. The wireless mode can reduce the cable deployment workload, costs, and time. Due to the control system deployed on the MEC for unified control, costs can be further reduced. This is the application of robotic arm control based on the highly reliable 5G network. Another scenario for remote control is using robots to replace human labor. Robots can replace people to inspect or do operations in harsh production environments, which reduce labor costs and safety risks. In this scenario, a larger number of sensors and cameras are required to collect the information and transmit it to the cloud through the 5G network. Therefore, the uplink rate must be higher than 50 megabits per second. As data needs to be sent back to control robots, transmission latency is also important. Based on the large bandwidth, wide coverage, and the low latency of 5G networks, robots negate the need for manual inspections and operations in complex and harsh environments. Upload HD images and the environmental data to the back-end platform in real time for analysis and processing, and generate alarms for safety risks in the factories. This is an example that robots replace humans to check and handle safety risks. The next scenario is about cloud-based AGVs. The AGV is short for Automatic Guided Vehicle, which has been widely used in industrial production and warehousing. 5G cloud-based AGVs can considerably improve the dispatching capability. There are many navigation modes of AGVs, such as electromagnetic, optical, and laser navigation. However, AGVs also face some problems. The first is the limited dispatching quantity. It is difficult to dispatch a large number of AGVs during the production process. Then, the flexibility is poor. Also, Wi-Fi-based AGV dispatching is vulnerable to interference and has security risks. Last, the costs of AGV are high. However, with 5G, what gains will the AGV bring? First, 5G with large bandwidth and low latency can support the AGV control on the cloud and provides networking capabilities, enabling scaled dispatching of AGVs. Unified control and dispatching on the cloud can also improve the cooperation, can also improve the operating capability. In addition, centralized control can considerably reduce the per unit cost of AGVs. This scenario also has some requirements on the network. 5G can be used with visual and laser SLAM to implement navigation. A great amount of data, including radar signals and images, needs to be uploaded to the control platform on the cloud. As such, the uplink rate is demanding. Has to generate control instructions and send them to the AGV. Latency also needs to be considered. For the coverage, only the factory or even just the corresponding production workshop needs to be covered. Therefore, we can see that cloud-based AGVs not only improve the dispatching capability of the system, but also reduce the per unit cost of AGVs. Next, the application is remote and on-site, AR and VR. This has been applied in some industrial fields. Here, we will talk about 4 scenarios. Digital design collaboration. Free from the 2D screen, designers can use AR and VR to display the design result, which delivers better experience and improves the evaluation process. Assembly operation assistance. During the assembly of high-end industrial devices, operators can use AR glasses to view the information and key points of assembly in real time, improving the assembly efficiency. Visualization for sales. Some exhibitions have applied this function. For example, during vehicle sales, consumers can use VR or AR glasses to view the appearance, interior decoration, and some key components of vehicles. This can significantly improve their perception of vehicles. O&M guidance. If new devices purchased from a vendor have some problems during the installation and the usage, the professional engineer of the vendor can provide remote guidance through AR and VR for frontline engineers. Therefore, 5G networks are required to connect to the frontline operators to the remote end. Frontline operators collect the information and transmit it to the 5G base station, which then is sent to the edge data center or the cloud. The remote and on-site solution improves productivity and operation efficiency, reduces travel costs in both money and time, and accelerates the cloudification of the industrial internet. Last, let's talk about how 5G supports high-density industrial IoT access. There are a large number of sensors in factory, such as meters, controllers, and location tags, requiring unified management. Through the wireless network, these sensors can be connected to the IoT management platform where data is processed in a unified manner. Data with real-time requirements can be processed by the local IoT platform and applications. while other data can be centrally processed on the remote IoT cloud platform. These differentiated requirements can be implemented with 5G networks. As an IoT scenario, it poses lower requirements on the reliability and the latency, but higher on connectivity. Therefore, 5G's massive connectivity is preferred, is perfect for this scenario to support a large number of sensors, and only 5G's massive connectivity can meet such a requirement. The above is new services and applications that are supported with 5G in the industrial production. To sum up, applying 5G in the industrial production will enable many new applications in future smart factories. Industrial devices can be connected to the cloud with the information management platform. For example, handheld barcode scanners can be connected to the cloud. Workers in the production line can use wearables to support the production process. Cloud-based AGVs can be used for warehousing and logistics management. Industrial cameras can be deployed on the production line for quality inspections, such as defect screening. The inspection robot can replace manual operation, improving efficiency. And robotic arms can be controlled by cloud-based PLCs for flexible manufacturing. This is a smart manufacturing solution that combines industry and 5G. We have gone through the whole course. Let's have a review. We started from 5G industrial applications and the development trend, and learned that 5G service deployment is implemented by phase, from eMBB to URLLC, and then to MMTC. Then followed the IOV solution, including its concept, service requirements, key technologies of CV2X, end-to-end solutions, as well as some typical cases. This is exactly the methodology of the industrial applications and solutions. After knowing the industry, you need to analyze the network requirements of the industry and also various services. Then, to address these requirements, you need to seek technical means and build end-to-end solutions to support service deployment. After that, we talked about the smart grid solution. In the power grid, there are 5 phases: power production, transmission, transformation, distribution, and consumption. Power distribution and consumption can be breakthrough points of wireless deployment, while other phases predominantly use wired communication, such as optical fibers. We can also leverage 5G large bandwidth, low latency, and massive connectivity to tailor various requirements in power distribution and consumption. Last, we came to the smart manufacturing solution. With the help of new ICT technologies, industry can connect to the cloud through industrial internet, achieving flexible manufacturing and improving production efficiency. This is the outline of 5G industrial applications and solutions. That's all for this course. Thank you.